One reason why you may like polynomials is because it's very easy to find the derivatives and antiderivatives. In this video, we're going to look at what happens when we have power series, in some sense infinite polynomials. How can we find their derivatives and antiderivatives? And we will see that, in fact, the same that applies to polynomials applies to power series, namely that to find the derivative of the infinite sum, we have to find the infinite sum of the derivatives, and to find the antiderivative of the infinite sum, we have to find the infinite sum of the antiderivatives. Let's look at the derivative case first. So let's say we have a power series, coefficients an, and then multiply by x minus c to the power of n. So we are saying it's centered around c, and we are summing from 0 to infinity. So we wish to find what is the derivative of this power series. And what I claimed, and I'm not going to prove, is that this is in fact the power series that has in each term the derivative of the terms of the original one. So an times x minus c to the power of n, derivative of all of that. When we are taking derivative of the terms, well, each term is a polynomial of degree n, actually monomial of degree n, and we have a constant an. We can begin by taking it out from our derivative, so an, and then we are going to have the derivative of x minus c to the power of n. So there's going to be n multiplying, and we're going to have x minus c to the power of n minus 1. Well, theoretically, we should also write x minus c prime, but that's just 1, so we don't need to write this. So going back here to the derivative, we have n times x minus c to the power of n minus 1. Okay, let's look at this. There is something weird here because I'm saying that the first value of n is 0, and then we have here power of n minus 1. That will give us something weird, but we just have to observe that the derivative I wrote here on the side, this is for n greater or equal than 1. For n equals 0, we are taking the derivative of an times x minus c to the power of 0. So we're just taking the derivative of an, which is 0. So we have no term for n equals 0. So we can write this as the sum from n equals 1 to infinity of an times n times x minus c to the power of n minus 1. So for this new power series, we would like to know what is the set of values of x where it converges. And what we can say is that the radius of convergence is the same as the one of the original series. So let me write over here, let's say this one an times x minus c to the power of n has r radius of convergence. Then the derivative of this is so this one, but with a derivative, also has r radius of convergence. The interval of convergence could change, so we need to check the endpoint of the interval c minus r, c plus r. So maybe a way of writing this is, okay, I know. Let's write here. We have c plus r, c minus r. I'm saying it's convergent all here. And I'm also saying that we need to check this point over here, c plus r, and we need to check this point over here, c minus r. Let's apply this to find the Maclaurin series for the function g of x equals cosine of x, using the fact that we already found the power series for sine of x. So we are going to consider the derivative of this power series. So we're going to have the sum from 0 to infinity. We are going to have the factor -1 to the power of n over 2n plus 1 factorial multiplied by x to the power of 2n plus 1, and here's where we take the derivative. This is going to give us the sum from 0 to infinity. And then we still have the same constants. And we're going to have a factor of 2n plus 1 multiplying and x to the power of 2n. Here, let's look. This 2n plus 1 is canceling with that 2n plus 1 here to leave just 2n, all of it factorial. So this is the sum from 0 to infinity. We have -1 to the power of n over 2n, all of it factorial, x to the power of 2n. So what is this? Let's look at the terms. When n is equal to 0, we'll get just 1. Plus, the next one is going to be when n is equal to 1, so x is going to be to the power of 2. It's going to be, we can change the sign here, looks nicer, minus x squared over 2. Next one is going to be positive x to the power of 4 or 4 factorial minus x to the power of 6 over 6 factorial. And we keep going like this. This is the power series representation for cosine of x. For sine of x, I hope by now you found that the radius of convergence is actually infinite. It converges for all real numbers. So for the new power series we found, the radius of convergence is also infinite. So this is for all x in the real numbers. And in this case, we don't have any endpoints to check for the convergence.